Hi, this is Dr. Liu. This is an introduction video for the for lenses. We have our optical rail here, and we have a uh, a distance of 1 meter marked as accurately as 1 millimeter here. So this is like a meter stick. And these are carriers, so you can slide them around, and each carrier has a groove right here that helps you read the position. You don't want to read the edges, you want to read the center. So here's a groove that points to 36.5 centimeters, for instance. We have these two that are lens carriers. So if you press down on both ends of this, and they open up the jaws, and you can place the lens inside, and then gradually close it just like this, so they'll hold the lens in place. So we have here a converging lens. We also have a light source. So it lights up with what we call the arrow and a lollipop because the optics itself it looks like an arrow and also a lollipop, and there's for good reasons. So then we also have another carrier that carries a screen. So we can imagine that the object is imaged through the lens and it shows up on the screen. And then we need to find out the distances. For instance, object distance is from here, where we also read from this groove, and that's where the face of the this object is lined up to. So the groove. And then we also can read the position of the lens to find out the distance of the object and distance to the image. There's no image at the moment. We're not trying to do that. So what we're trying to do here is to find out the focal lengths of these lenses. We have two converging lenses, and you can test them out just by looking through them, see if they magnify anything. If they do, they're converging lenses. We also have two diverging lenses. We only need to use one of them. I like to use this one that is more diverging. Basically, if you look through that, it is it magnifies image a lot more than the other one, so you can tell which one is more curved. So I like to use the one that magnifies image a bit more. Just need one of them, and you also have a couple other accessories. This is a little mirror, and here is a little well, what is this? This is just mm, an object. I say it's just an object. All right. So then this is shared. We have a little telescope, may look slightly different. So it's just a telescope that we can extend. And I've already done the work. I took it outside and looked at a faraway object, and I made sure that I was able to focus on the faraway object, and I don't want to move it anymore. It does move, so just make sure you don't move it. If you suspect you have moved it, go outside in the hallway and look at something that's down the other side of the hallway to focus on it. So that's that. Let's place it here so it doesn't roll away from us. Okay, so the next things will be to find the focal length. Um, So there are multiple ways of finding the focal length. So the first way, let me grab my lab manual. It's right under the the webcam. Okay. So the first way we're going to do is to form an image, basically using assuming that light ray is coming from far away. So this side has to be very far. That means move this as far back as possible. You're not reading the coordinate of this thing, so it's okay if it goes off that 0 meter range. And then also move that as far back as possible, but still you have to be able to read the position. So I suggest put it at 1 meter. Okay, so that's 1 meter. And what we're going to do is we need to turn the lights off, right? And we're going to form an image pretending that this object is from very far away. Even though it's not, it is okay. We just pretend that it's far away. So I'll turn the spotlights on and turn the ambient lights off. All right, so we're good. We can still see something. Um, I'll dial down the spotlight a little bit. It was just, oh, okay, here we can even see the shadow right here. And what we're trying to see is we're moving the carrier that carries the lens until we see a clear image right there. Will be the arrow and the lollipop image. It'll be a lot easier if you do this in person instead of watching the video. So I'll just slide until I get a very nice, ooh, very clear image. Okay, now it becomes less clear. Just slide back and forth. Only care about the center. When you see the lollipop in the middle, you can tell whether the lollipop's edge is very sharp. Don't worry about the halos around. Okay, so now I think I got a good idea. Um, it's a very small image. Let me see if I can show that on the video. There we go. It's not clear, so let me do an autofocus. Okay. Yeah, I just don't think we can focus on that well enough. Maybe it's just because the camera cannot focus too close. So it's actually quite clear right there, except that the autofocus didn't do its job too well. So you're looking for that image, and now you have it. You need to write down the position of the lens. We already know the position of the image is at 1 meter. So just do the position of the lens, and okay, I'll be reading right here. Let me move that out. So I'll be reading the position 85.7. So I'll write it down. We have Excel here. Three, three focus. So 85.7, and also record down the position of the screen is 100. Okay, so that's for one lens. Okay, I'm going to switch over to the other lens. I have this other lens. All I have to do is to grab the edge of the lens. Don't grab it by the middle. Grab the edge and press this down to release the jaws. And put this one in. Okay, so I'll do the same thing. I'll look for a clear image. Looks like, oh, this one has a longer focal length. Okay, yeah, maybe I can focus on this. Okay, this is where I definitely lose the clear image. There's a wide range where I can call the image is clear. That's unfortunate, so I just have to slide back and forth and try my best to tell. Maybe it's over here. Yep. Maybe the next time will be different. So let's turn down the light and see if we can get this. Okay, this is actually a little better. See that? It's actually quite focused even on the camera. And I've moved back the housing quite a bit. Well, this does depend on my own decision whether I see, oh, that's clear, focused, or I move back and forth again and try to discover the position. So it is a bit more up to the individual experimenter. So position wise, 51.8. So 51.8, and also the image is 100. So the distance between the two will be the focal length. Okay, so that is one method, basically using parallel ray. And another method is going to be using the telescope. So um, so here's how to use the telescope. Um, we're going to take the telescope over here, look this way, and this way is where the image the object is. So we're looking through the telescope with the lens in here and move until inside of the telescope we can see a clear image. Okay, So here's what I'll do. I know that this is moving out of the range. Um, I'll pull this further back. Um, yeah, probably back on the center console where I can kind of look down. Okay, so I think I can see a bit more action a bit further away. Okay, so I'm going to remove the screen and I'm going to look this way. And as long as I can see a clear image, I'll stop moving that lens. It doesn't matter how far I use the telescope. So if I'm by myself, I have to get somewhere close. So I have this within my arm's reach, right? If I'm with a partner, I can easily say, okay, move further, move, stop, or move back a little bit, right? So I'm just by myself. That means I'll have to do this close. So this is what I do. I think I'll get a relatively clear image because the focal length that I measured previously was what? Close to about 50 centimeters. This is about 40, so I'm close. Okay, just, okay, I was looking. I wish I had a bigger, okay, how about this? I'll move my head until without the telescope I can see the image in the middle. And I do wear corrective lenses, so I need to put my. Now I see the image in the middle. It's not very focused, and then I move in the telescope. There we go. Okay, this is very clear, but on the other hand, I think the distance might be a little too close. So I'll try to readjust my telescope in the hallway. I may have touched it already, so let's see. Okay, I have an exit sign on this side. I'm gonna have to walk to the opposite side to focus on the exit sign because it is a clear enough thing. So I might lose connection to the LDU. Okay, don't know if you can still hear this, but the other side's exit sign is very dimly lit. I think that's probably against OSHA code. So trying to get a faraway image to focus on my telescope. Okay, I think I should probably use my corrective lenses, but it shouldn't be too bad. Okay, so I'm back with the adjusted telescope. This still is a not very accurate method, by the way. We have better methods down the road. Okay, I'm placing this in. Yeah, I guess this is this is it. Oh, by the way, the position of the source is not at a readable position. I'm going to move it to 0 centimeters. That means I need to readjust the position here. I'm looking at the center of the cross, which is the image. really difficult to tell the exactness. Okay, I think I'm good. The position is 24.3. So I'm going to group that together with this, the second lens, and I'll replace it with the first lens and redo this process. Unfortunately, this doesn't really provide a very accurate result either. But let's finish this part. Okay, I see something here. Try to look at the middle of this and then put in the telescope. Okay, not good. Now I'm getting more focused. Okay, very nice. Out of focus. Okay, here it is. Okay, I got it. 11.8. Okay, just to see how far these values vary. Trying to pretend that the light source is far away, I get 14.3, and using the telescope, I get 11.8. So 14 versus 12, well, we're maybe 20% apart from the average. And pretending the light source is far away, apparently it's not very good because um, I have a 51.8, so it's about 48 centimeter focal length, and the other one I got a 24, so quite a far apart. Okay, so let's move on to the next. We're going to use parallax in order to do this. So all we have to do is now we can turn the lights back on. All right, so let me do that. Okay, so the lights are back on, and then we're going to view some objects. So the object is this a little hook thing. Okay, so this little thing here. And we're also going to place a mirror. So here's how it's going to go. A mirror and a hook in front, and then a lens in front of that. So we don't really need the light source. I'll unplug it. Okay. And how about I remove the screen because the screen is sitting as low as possible. That's easy to restore the position, the height. So I'll put that in there. I'll put the mirror in and then line up the two so that I know the two will be roughly the same height when I secure the mirror. And I'll do the same here. I'll remove that lens holder and place this object here. And the object is supposed to be halfway. Basically, the top should line up with the middle of the mirror. Kind of difficult to make that line alignment, but that's okay. Doesn't have to be. Okay, so right here. Okay, so now what happens is if light comes out of the object, diverges, and hits the lens and becomes parallel rays, they'll hit the mirror and the parallel rays return and then focus on the same exact position. So this means if you look from this way and move your head from side to side, you won't be able to see the image and object moving apart from each other. This may be difficult to record, but at least you can see what I'm doing here. So I know this thing's focal length is probably around 12 centimeters. So let me fix this to a fixed position. How about I move it to 40? And I'll get the mirror close because the closer, the easier to catch the light instead of having a lot of scatter. Okay, so now I'm going to move that back and forth while looking at the image, looking this way at the image and also the object, and move my head side to side to see how the image and object moves against each other. As soon as I see them move exactly in sync, I stop moving the carrier. That's where the focal point is. So, okay. So I see the little thing. It's like a paper clip, but it's actually just a um, kind of a bent wire, a metal wire. So this is already pretty good. They're moving together. Maybe I just hit, yeah, I actually hit 51.5. That's 11.5. Maybe that's the exact. All right, I'll move it out of the way. So I'll move out of the way. And okay, I don't really like it because the thing doesn't really line up with its image. I'll try to move it up so they try to touch each other, image and object, and also the lens may need the mirror may need to be adjusted a little bit so that horizontally they're lined up, and vertically I can line this up by moving that up a little. It's like, they're trying to reach each other. Okay. Yeah, if I move around, my object is moving faster than the image. Okay. So if I move this further out, my object is moving even faster than the image. Because parallax, right? It's closer. The other one's further away. It has less of that. So if I move so close, and then my image starts to move faster than the object. Okay, so if I just get to the correct distance, they start to really move together almost. Um, get them really to touch. That makes it easier to see. I think the image still moves slightly faster. That means I need to move closer to myself. I see this is good. All right. So I have a 40 and a 52.2. So I recorded. This is the first lens. 40, 52.2. So that means a 12.2 centimeters of focal length. Okay, I'll do the same thing for the other lens. This lens has some unknown focal length, probably further than 20 centimeters. So they'll take some struggle further back, right? Still at 40. Okay, I can't really see. Okay, yeah, I'm too close. Still too close. Oh, there I can see. Now I can see it. Okay. So now the object is faster than the image. That means I'm too far away. Almost the same speed. Object still slightly faster. About the same speed. Object slightly faster. Okay. I think I'm just holding the lens slightly more twisted. Um, okay. Okay. How about I move closer? Try to make the image move faster than the object. Yep, I got that. That means I need to move further back. Image slightly faster than object. Oh, slightly faster. Now they're in sync. Okay, so finally mystery resolved. This is a better accurate method finding the focal length. What is it? It's 20, is it 40? So from 40 centimeters to 65.4. So 25.4. That's like 10 inches. Okay, so which method was slightly better? Well, it was the telescope method because at least we're focusing on something really far away along the long corridor direction. We have, well, this is a short corridor, I'm sorry. At least we were looking at something that's 50 feet away. And over here, when I'm assuming this one is very far away and my lens is right here, that's not very far away. This is a bad assumption, right? Okay, so now we have that. We'll have one last method to find out the focal length. This is called conjugate foci. So the way to find conjugate foci method is we're going to turn the lights off again. I'll remove these two things that we can only see when the lights are on. And I'll place the screen in. I know the screen is basically dropped all the way down. I know the height. Okay, so I have the screen back, almost invisible because against the white, uh, yep, there, the white wall, the painting. Okay, so now here is what I'll do. I'll also remove that. I have the object which I'll plug in. I have this, and I'll just kind of hang back. This is a large focal length, right? 25.4. So I can barely make it through the whole distance because the conjugate foci method would require roughly 4 focal lengths of distance, and this is maxed out at 100. So 25 times 4 is 100. So we may not be able to use that method for this anyway. So let's hope that we can, because these are already set as far as possible, 1 meter apart. So the conjugate foci is this way. I can't really do it, but I'll pretend I was doing it. So I can kind of see the image. Okay, so I'm looking for images. Okay, yeah, very close to the middle, so I won't be able to use this method at all for this lens. So I'm right here, and here's an image. Well, you can't really see it, but I'll dim the light later. And then try to find another image, well, which was almost exactly the same location anyway, so I can't use this method on this lens at all. Then what to do? Well, okay, I can use the other lens. So the other lens will be a lot more dramatically improved with this method. Okay, so yeah, there we go. Very large magnified image, and then extremely minified image. Okay, so maybe a little too far. That means maybe I should bring the screen in. Say, let's bring it in to only 80 centimeters apart. Okay, so now we turn the lights off with the spotlight on. Okay, lights are off. Let's make some images. Okay, there's an image. There we go. See that? We see a magnified image when the lens is closed. So we'll read the lens position, and then we'll move towards the screen until we see another image. This time is minified. Okay, it's got a minified image, a little cross. So we'll measure this position again. So the calculation would involve the distance between the two positions, the conjugate positions of the lens, which we recorded, right? And then also the distance from the object to the screen, the image. So that is, we had that at 80, right? So I'll record only for the first screen. I have 0 for the object, and let's see, what is this position? I need to turn off the lights a little. 65.2, and 80 is the image position. I just need to find the other image again over here, dimming the lights. Okay, here we go. Okay, here we go. Let's read the position. 14.6. Okay, so I hope you know why I cannot do that for this other lens, because they'll be exactly 0 distance because of the focal length itself is 25.4. Okay, so I'm skipping that. All right. And the next part is finding the focal length of a diverging lens. I have two of them. I'm going to use this one that is minifying more. Okay. So the way to do it is first you find an image. So object image relationship with a lens. Um, which I'll try to move this to a little closer, maybe 70 centimeters, so the image wouldn't be too big and difficult to focus on. Mm, Okay, I just moved to 60 centimeters, and I have a rather clear image right here. Okay, so here it is. Basically, the image shows up at the 60 centimeters, and that image itself can serve as a secondary object because light is focusing over here. After this point, light will be diverging again, just like where the original object is doing, except that it's less bright. So we'll catch that light before it makes the image, and see that it's already fuzzied up. So all we have to do is we record this position. We already gave it a position of 60. So we'll record that position for object. The first object right there, the box is 0, and the lens is at 16.3, 16.3. Make sure that you put everything in so you can always recall where the positions are. And then the image is at 60. I set it there. Okay. And then I want to put in mm, the diverging lens, and I'll do another lens carrier and set it up here so that I can have roughly the same height. Okay, here we go. And I'll put the diverging lens in. Okay, apparently the sharp image is gone. So what do? I just move that back until I get the sharp image. But I also want to record the position of the diverging lens. How about I make it easy for myself and place it somewhere that I can easily read, like a nice number. It's 26. How about 30? One way to read the groove is if you look at it, it's really dark, but if you bring your hand close, it reflects some light. It actually lights up the groove a little. So I place it at 30, and I don't have a clear image anymore. I'm going to move my screen back until I get a clear image. Okay, looks like maybe that was placed a little too far. Okay, how about I make it a little closer? See if I can get that image. Um, you know what, maybe the diverging power is too high. It will not do at all. So I'll use the other diverging lens instead. Okay. Yeah, I can certainly find a clear image this way. Okay. Yep. I can certainly find a clear image this way. So where did I put the diverging lens? Need a little more light. I'll place it at 44. Okay, I placed diverging lens at 44. Turn down the light so I can get focusing on the screen. I'll move the screen. That's not very clear, kind of fuzzy. there's quite a bit of range because imaging depends on your own way to tell whether it's clear or not. Okay, so the screen is at 86.3. So 86.3. Okay, so what about the this one over here? Because well, the I wasn't able to see anything, and because its diverging power is too high. But I can also try it, get it further away. See that? I was able to see something. Okay, unclear, a bit more clear, but see the difficulty is always telling when exactly you see the most clear image. So roughly over here, I'd say, okay, roughly over here. So I'll record that position, those positions. So I still have the same exact light source, the first lens, and where it makes its image. And then my second lens now is located at 52.2. And my image located at 78.6. 78.6. So, okay. Okay, I think I have gotten everything. Well, wouldn't it be better if I had a better way to use the mirror, right? Use the mirror in order to get the diverging lens's focal lengths, because I consider the mirror or the auto collimation method the more accurate method among all the other methods. Okay, but anyway, we're done here. So the rest is just calculations.